Hello and welcome. I'm Bauke van der Velde. Today I will be talking to you about time frequency EEG analysis, especially what can add to other existing EEG analysis methods. And I want to start with a short recap. And first, let's just start with a recap on why EEG is important. And I find that this slide is very important, and it's kind of directly the take-home message of this whole talk. Um, and I want to start with this most notably because when I ask students or fellow researchers why they would use EEG, usually I get a wide-ranging type of answers that range from, well, it's easy to use with infants, or they usually say, well, it's very useful to use as a sort of preliminary study right in front of your big MRI experiment, your big fMRI experiment, in which you first find out where in the brain there is a direct stimulus and response relation, but then you go more into depth, more into detail through fMRI. Or they tell, well, it's very cheap, so why not? And while all these uses can be very valid, I feel that they kind of completely ignore the most important aspect of EEG, and you know about this aspect, but I feel I want to press upon you even more and more and more today that the temporal resolution of EEG is something incredible, and that we should use this to the fullest extent, so that you can come up with very specific paradigms in which you can only use EEG, which gathers us new types of information on how information processing is done in the brain. So let me also give a short recap on ERP. ERP, Carlijn already told about gave a short lecture about ERP, and during this lecture she told about averaging EEG signal over trials. And basically what this means is that when you record EEG, someone is watching a particular stimulus, or there is a particular stimulus, and you repeat that multiple times over the complete experiment, and then at the very end you cut your EEG data into equal pieces of equal length, which start with the stimulus and then a certain amount of time afterwards, and you average these signals, right? And the idea behind this averaging is that you remove any sort of data that is not directly related to the stimulus. So you remove noise, but you also remove background EEG data, background brain data, and what is resulting is a sort of representation of the brain, which is very much locked in time to stimulus presentation. And you have all these different characteristics, which you can also see on this image. On the left side, you see the different trials, and all the trials are quite noisy. And then when you average them together, they all get this sort of same characteristics. For example, you see a positive peak, a negative peak, and then a positive peak again, a negative peak, and then a positive peak again. And these characteristics, and especially if they happen or not, or when in time they are happening, are usually correlated to behavior. And while ERP is therefore very resilient against noise, and you can get a very clear stimulus and response loop into your data, there are a couple of negatives about ERP. And this is basically the first thing I want to ask you. And after this, the lecture will go on pause, and you can fill in your answer in screen at the website. And I want to ask you, well, now you know the advantages of ERP, because we already had 2 lectures on ERP, but what are the most important disadvantages of using ERP as compared to other EEG analysis methods? So I'm not looking here for answers like ERPs don't have a very good spatial resolution, because we know that. But if you compare it to other EEG analysis methods, so if you think about what type of information there's completely in the ERP data and what type of information you lose, what are the most important disadvantages of using this ERP? Well, the main disadvantage is that you lose brain activity. So you lose real brain activity through this averaging over time. And there's 2 specific possibilities when this happens. One is the response is not related to a specific stimulus. So, for example, you could come up with paradigms like a reading paradigm, in which children are asked to read a long passage for about 5 minutes, but there's not really a specific stimulus. You could maybe bind the word together with the stimulus presentation, but it doesn't really work that way. It's more like the total reading. What kind of brain activity uses the reading of a passage? So therefore, you cannot really average anything. And if you do, you probably also lose the real brain data which is used with this reading paradigm. And the second reason is the response could possibly be related to the stimulus, but is out of phase. And I want to give you an example of this, and this is a very crude example. This is an example that I just created. This is not an example that you will find in the brain, but let's imagine that we're doing a working memory task, okay? So let's imagine, okay, just try to keep as many numbers in your head as possible. 5 numbers, 7 numbers, it doesn't necessarily matter. And this is the trial data, this is the EEG data. And the EEG data, just as Carlijn already told you, EEG data is basically a recording of a population of neurons. And this population of neurons you can find under the respective side. So this is on the left side of the brain, left frontal side of the brain with the F7 electrode. And you see here's the stimulus presentation, and then there's normal brain data, and then after a while, halfway through the trial, this enormous wave comes up, which probably conveys some information. Why? Because it's very pronounced. And now we look at trial 2. And trial 2 has, again, sort of like a random movement here, and then again, a very pronounced wave comes up. So it's very similar, but if you look closely at both waves, you see that they're actually completely mirrored. So here you have a peak, and there you have a trough, and here if you peak, and there you have a trough. So if you average these two together, and let's do that with 2 more trials, so let's add trial 3, which is similar to trial 1, and trial 4, which is similar to trial 2, and let's average these together, you see actually that at that specific point in time, there's no information whatsoever on your ERP. Well, that's not necessarily true. That's not really fair, because this very specific wave pattern is simply slightly out of phase with each other. So the amplitude is not the same, but the wave pattern is actually the same. So how can we overcome this? Now, well, the good news is that yes, we can fix this with other analysis methods. For example, time frequency analysis, in which I will go into more detail today, which is you get these brilliant pictures right here, or with a connectivity analysis, which I will talk about in a lecture after this, in which we talk about functional connectivity between electrodes. So how can we determine which 2 electrodes are probably connected in a way, or which 2 populations of neurons that you can find under electrodes are connected in a way. So let's first go back to the EEG recording, right? This is an EEG recording. And let's say that this EEG recording is recorded at the FZ side, so it's somewhere frontal. And the funny thing about EEG is that you can pull this sort of data, you can pull it apart into different waves of different speeds. And here we have, for example, a little bit more of delta, so you see that here as well, right? You see that returning there. And delta is a very slow wave. So every 1 second, you basically have a total wave, right? And then we also have a little bit of theta, right? You see the theta here as well, these sort of waves here. It's a little bit quicker. So it's 3 to 6 hertz, 3 to 6 times per second, it's a theta wave. And then you have alpha, and alpha is even quicker. And this is typically between 6 and 12 hertz. So this kind of depends whether you're an infant or not. Infants usually have between 6 and 9, and adults usually between 9 and 12. And we also see some beta waves. And the beta waves are between 12 and 25. And there's also gamma waves, which is everything above 25 hertz, which is really, really quick oscillations. And all these waves you couldn't possibly detect with any other method than EEG or MEG. Right? If you compare this, for example, with fMRI usually only can find very slow waves because we have to wait on the bolt response. So they usually can only find waves of 0.25 hertz and lower, and oftentimes it's even lower than that. But apparently all these waves are also apparent in our EEG signal. So I've been talking about waves a lot, and just to make it a little bit easier, usually now when I'm going to talk about waves, I'm going to talk about oscillations. But what exactly are oscillations? An oscillation is a regular variation in magnitude or position around the central point. And this is kind of dry. It's kind of like what it means. But basically, it just means that it's everything that goes back and forth, and that makes an oscillating pattern. And to look at probably the most simplest oscillation in existence, the sine wave. The sine wave actually starts at 0 and goes up all the way to 1. and it comes down all the way to -1, and then comes back to 0. And this is like one full oscillation. And these oscillations have certain characteristics. Firstly, they have an amplitude. An amplitude, you can measure the amplitude at every given point in time, and it's simply the height of the signal. So you measure it along the y-axis. So here it's about 0.7. You have max amplitude here of 1 and a minimum amplitude here of -1. You also have the period, and the period is usually measured in time. So how quickly do we complete one oscillation? And very closely related to period, and people usually talk a lot more about this term, about frequency instead of periods, is the inverse of the period. So that's the frequency. So 1 over the period. So let's say we have a period of 0.2 seconds. So that's 5 times a second. So the frequency is 5. And lastly, you also have the phase of the oscillation. So where exactly the signal is in this oscillation, that's actually the phase. So relative to the oscillation where we are, that's the phase of the oscillation. The phase of the oscillation is represented from 0 to 2 pi. So at the halfway point it's pi, at the end it's 2 pi, and at the beginning it's 0. And the peaks are usually half pi and 1/2 pi. So now you know a little bit more about oscillations. We can now look at this specific slide, and we see, okay, so apparently this EEG recording has a lot of different oscillations with different frequencies, which are depicted back here. And they can differ in amplitude, but they can also differ in phase, or where they are in their oscillation. And one of the first mathematicians to suggest that, one of the first and the most important mathematicians with these sort of oscillations was Joseph Fourier, and he opted that any signal can be reconstructed by adding together oscillations of differing phase, frequency, and amplitude. So this means that you can basically add as many sinus and cosinus waves as you want, and then after a while you can get signal which is as detailed as an EEG signal. So this begs the question, if any signal can be made out of oscillations, are there truly oscillations in the brain? Or is it simply that it is a random signal and there's always oscillations in the brain? So the only reason why so we need to find evidence whether or not there are really oscillations in the brain. And one of the first starting points for this is, are there mechanisms in the brain that can actually induce these oscillations? And do they? And there's two different mechanisms. And the one is the simple system, and the simple system uses a pacemaker method. And the simple system are usually motor neurons, or they are involved in reflexes, where one very long neuron goes all the way through the spinal cord, and it projects onto one other neuron, and this neuron also projects on another neuron. And usually the oscillatory patterns in these neurons are usually instigated with one single neuron, which works as a pacemaker. And the pacemaker bursts on and then stops, and then bursts and then stops and then bursts again, and therefore is a kind of like an oscillatory pattern. However, if you look at more complex systems, they usually you can have these whole models of different neurons working together, and inhibition is here sort of the central key factor which creates these oscillations. And here we have a schematic of the several layers in the neocortex, and you can see, and it looks a little bit detailed and a little bit fiddly, but the two main things I want to make your attentive of is that on the left side of the screen you see the red neurons, which are the excitatory neurons, so they make the area more active. They also make all the neurons on which they project more active. And you see on the right side, you see the inhibitory neurons, which are blue, and they make the whole area less active, right? So if they become active, they project inactivity to other neurons. And you can see quite clearly instantly that if, let's start at a completely random point in time, and if these neurons here are active, they project onto themselves, but they also project onto these inhibitory neurons. And these inhibitory neurons then become more and more and more active, and eventually they overpower these excitatory neurons. and therefore the power will go back down, right? And then when the area is all the way completely down, then the inhibitory neurons obviously are themselves also inactive because the complete area is inactive. And then the excitatory neurons can fire again and therefore become more active. And this happens time and time again. So this in turn means that if you go in an oscillation and if you go up and if you are at the top, it's very difficult to excite that area. Why? Because the inhibitory neurons are very active. So they really rein in the activity that these excitatory neurons can do. However, the further you go down, especially in the trough, all the way down at the bottom point, the area is actually very reactive and can be very easily influenced by outside activity because these inhibitory neurons are themselves also very inactive. But can we also see these oscillations simply online in the brain? Can we see them more clearly than this jumbled up EEG signal that we just had? Yeah, well, you can. And let's do a very simple experiment in which a participant is seated in front of a screen. They don't have to look at the screen, they simply have to sit down. And we're doing an EEG recording, and we're recording specifically a visual electrode. So this is OZ. So this is an electrode which measures populations of neurons in the visual cortex or in the occipital cortex. And the simple task that the subject needs to do is simply close your eyes and open your eyes. And close your eyes and open your eyes. And you can see this action very clearly in the visual cortex. So this is a representation of this eyes closed versus eyes open paradigm. And this is just one electrode. You see here when the eyes are open, you see that this is sort of an irregular signal with some small, the amplitude isn't that high. You have a bit, sometimes they're a bit quicker, so that you have a little bit of higher frequency data there, but you also have these very slow waves in there. But when the eyes are closed, at the moment that the eyes are closed, first thing what happens is that there's this huge increase in alpha oscillation. And it kind of like diminishes any other type of activity. So what basically happens is that this alpha oscillation inhibits any sort of visual activity in the visual cortex. And why is this necessary? Because there's simply no visual information. So the brain doesn't want to have any information. So this alpha oscillation just arrives and it stays there until you open your eyes again. You can do this yourselves. If you want to do an EEG experiment, the first thing you can ask, okay, just close your eyes. You can see that instantly on the screen, but only in the visual, at the visual electrode. So only on the back side of your head. So that's right here, which implies that only the visual part of the brain has this alpha oscillation when your eyes are closed. So now we know that there are oscillations in the brain and they can be made, but we still don't know why they are so important and why does information get relayed from a brain area to brain area in oscillatory patterns. And the main thing that you want to focus here on is that it improves communication in the brain. And it improves communication because by synchronizing oscillating patterns, brain areas improve their consistency in communication. For example, if you have one specific brain area and it oscillates in a particular way, and the other brain area oscillates in the same particular way, if these two brain areas communicate to each other, one brain area can say something at this particular point in the oscillation, and it will always create the same effect in the second oscillation. So if two brain areas are completely out of sync with each other and oscillating completely different patterns, then one time this sort of information from brain area 1 would convey one meaning, and the other time maybe it doesn't activate something at all. So that won't work. So these oscillations are very important for consistent communication. It also improves efficiency in communication. And this goes back to what I was telling you guys about earlier, and that is that in the trough of the brain area, the trough of the oscillation, so if the oscillation goes down and then we have the minimum peak of your oscillation, that a brain area becomes very reactive. So it can become active very easily because the whole area is sort of lowly active. So if you notice, based on that your oscillations and the other oscillations are synced, you know when to send the signal in order to generate the biggest response from the second area. And therefore, you don't need as many different responses, but maybe only one or just a very short burst just at that particular time, which improves efficiency in communication. And lastly, it gates information processing. Say you have two areas that are right next to each other in one area, and areas that are right next to each other are highly interconnected. Say that this one area is basically communicating with itself. So all the neurons within the area are communicating with itself, but also they also have projections to other areas, but they oscillate in different rhythms. And the chances that that would then get a response of some sort are way lower, and therefore it gates the information processing, which makes the information processing a lot more robust.